Hello physics students, welcome to what should be the last, or what is the last of our videos in the introduction and revision section. And in this one we're going to look at momentum, work and energy, recapping some of the physical science stuff but introducing a couple of new things. We'll try and go through it as quickly as possible because we don't want these videos to be too long, but we still have to say what we have to say. Alright? Now, so in momentum we have exactly the same formula we used last year for momentum, P equals mv, where momentum is in kilograms meters per second because the mass is in kilograms and the velocity is in meters per second. Now on your physical science sheet you had a slightly different arrangement of this, but in the physics sheet we have this, where the force net equals, triangle means change in, now mv is obviously the momentum, so this statement here is the change in momentum, and although it says mv, we could have u there, they're interchangeable, and so sometimes in physics we don't always state all the possibilities because there's an assumption that you can work out that v and u are interchangeable depending on the situation. And delta t is the time interval over which this change in momentum occurred, and that all equals ma. Now on the physical science sheet it looked like this, okay, where you have just this expanded a little bit without the triangles basically. So if you're surprised or not aware of this, this equals this. Okay, now with momentum, of course, we learnt the law of conservation of momentum, and that is the change in momentum is equal to the final momentum minus the initial momentum, and momentum is conserved. That's basically what it's stating. So it can be written like this: the change in momentum equals the final momentum, initial momentum, mass times the final, minus the mass times the initial. Now, a term that we didn't use too much, and it doesn't get used all that often, is impulse. And impulse is a term that we use in physics to describe the change in momentum. And so, because we can recognize that this bit here, is the change in momentum, what causes the change in momentum is a force being applied over a period of time, so Ft, and it's the Ft that is actually the impulse. So Ft is equal to the change in momentum because we ask ourselves what causes the change in momentum. It's a force being applied over a time. Now there's no special unit for impulse, and in fact the symbol we use for impulse is Ft. So if you're asked to solve for Ft, that's solving for impulse, or if you're asked to find the impulse, you rearrange your formulas to get F times force times time. Okay, and the units for it is just the same as momentum. Sometimes it can be referred to as a Newton second because obviously force is in newtons and time is in seconds. So you must sometimes see that one. Now on a force time graph, the impulse is equal to the area under the graph, which is a useful thing to know because we sometimes give you force time graphs. And so for this guy you just work out the area of that triangle. And I think they got 40 Newton seconds. Now the law of conservation of momentum, which we mentioned before, is of course only applying to a closed system. And by a closed system we're looking at the individual situation that we look at, and not the complete situation that happens in the universe. So when you collide two cars, trolleys on a bench top, we only look at those trolleys. We don't look at the impact that has on the fact that the Earth is rotating, and the Earth is rotating around the Sun, and the Sun is actually moving through space. And so we don't look at the mega stuff, we just narrow it down to our little system, we call it. And of course it says that the total momentum before a collision or explosion, remember in physical science we looked at collisions and explosions, equals the total momentum after the collision or explosion. And for explosions we had our bomb at rest and then it blew apart, so this initially has no momentum and then we have two pieces that have momentum, but because their velocities are in opposite directions and momentum is a vector quantity, those momentum should cancel each other out. And collisions, where we can be grouped into two types: the rebound, where they bounce off each other, gas molecules, billiard balls, or coupled, where they lock together, a bullet in a target, or what else? A bullet in a target, trains coupling, or shopping trolleys linking together, things like that. Now, you also need to know the difference between an elastic collision and an inelastic collision. An elastic collision is a collision in which both momentum and kinetic energy is conserved. So there's two components in a collision. There's the momentum, which we were talking about, but these bodies, because they're moving, also have kinetic energy. And in an elastic collision, they're both conserved. In an inelastic collision, the kinetic energy is not conserved, because there's no law of kinetic energy. There is a law of the conservation of momentum, but there's no law of the conservation of kinetic energy. So billiard balls, you've probably played billiards or pool, or you know what that's about, or if you watch football or any of the contact sports, these are examples of inelastic collisions, because the kinetic energy is converted into other forms of energy. Now, you might argue that the billiard balls aren't truly an elastic collision because some of the energy is converted to sound and a little bit to heat, but we conveniently ignore those when we look at our own little system. Okay, so let's just quickly go through a couple of examples of these sorts of things that we need to think about. Here's a problem. We have two balls of equal masses m and equal speed v engage in a head-on collision, so effectively one has the opposite but equal velocity. That's why it says equal speed. What is the final velocity of each ball in terms of m and v? Now, if you imagine two masses, two balls going at equal speed, hit each other, and it's an elastic collision, the kinetic energy must be conserved and the momentum must be conserved. So they've both got a bundle of energy, they exchange their momentums, and they bounce off with an equal but opposite velocity. And hopefully you can picture that. No calculations because there's no numbers. Here's some numbers. Two balls, each with mass 2 kilograms and velocities 2 meters per second and minus 3 meters per second collide head-on. Their final velocities are minus 2 meters per second and 1 meter per second respectively. Is this collision elastic or inelastic? Now, you might be able to already guess that it should be an inelastic collision because these velocities are equal but opposite to these velocities. But we need to verify that. The momentums will be conserved, but the velocities will not be, and the kinetic energy will not be. So, to check for elasticity, we calculate the kinetic energy both before and after the collision. Before the collision, the kinetic energy is, using half mv squared, 13. That would be in joules, of course. After the collision, it's 5 joules. So we've lost kinetic energy. And since the kinetic energies are not equal, the collision is therefore termed as inelastic. Two balls mass m1 and m2 with velocities v1 and v2 collide head-on. Is there any way for both balls to have zero velocity after the collision? And clearly you should be able to picture that situation. And we've done that with our trolleys and things, where we rolled them across benches and they collide and they just stay still. But it only happens in very specific cases, doesn't it? And so to find that, first of all, the collisions must be inelastic, as the final kinetic energy must be zero. And so the kinetic energy before is not equal to the kinetic energy after. So energy gets lost. It must also be completely inelastic, as both objects have zero velocity, and therefore they must stick together. And so the final momentum of the system is zero, as neither ball is moving. Thus, the same value must be true before the collision. For this to happen, the momentum, and we see it here stated here, since both masses are equal, the momentum must be equal but opposite. So the mass 1 times by initial velocity 1 is equal to the minus of mass 2 initial velocity 2. Okay, and the minus is there just to make sure it all cancels out. Thus, in a completely inelastic collision, both masses will be stationary after the collision. So basically the momentums cancel each other out. Okay. Now, conservation of momentum in 2 dimensions is something we didn't do in physical science. It gets a little bit more complicated because it involves a little bit of maths. Here's an example, and this is not recommended, do not do this at home. An empty spray can of mass 120 grams rests on top of a fire and explodes into 3 fragments. One fragment, so we're told all the information, the 30-gram fragment travels to the east at that velocity, a 20-gram fragment moves south at that velocity, and then you've got to work out the third piece. Now, because of the conservation of momentum, we can recognize that we can draw this diagram here with our momentums. So there's our can, there's the center of mass, and we're drawing the momentums from that center of mass. So we have P1, P2, and P3, and we can work out P1 and P2, and we can then, knowing that these momentums are conserved, they should form a triangle head to tail. So we put one momentum down, then the other momentum, and then we get P3 should be the hypotenuse, and we've got a right angle triangle, fortunately, and generally speaking in these questions we'll give you a right angle triangle. We can then use Pythagoras and trigonometry to work it out, and that's what they did. So they worked it out to be 2.7 as the momentum, and therefore knowing the mass, recognizing this is grams not kilograms, being careful of course, we have that velocity of 38.4. Now we need the direction because it is a momentum, and so they use trigonometry to work out that angle, which is north, and then 42 degrees swinging around to the west. You could also have stated it, if you're into orienteering or bushwalking, you might recognize that that is also can be given as a 3-number bearing, which is 318, or 318 degrees true, if you want to put it all there. Alright, another question. Here we have ball A, 2 kilograms, travelling at 10 meters per second, strikes a stationary ball. Ball B moves off in this direction, ball A moves off in that direction. Okay, you're given an angle there, you're given the initial momentum, the two momentums must equal each other. Can we work it out? Yes, because the momentum is conserved, so it makes a nice triangle. If you're given a question like this, and sometimes they do, and the momentums do not make a triangle, that means momentum isn't conserved. It's being lost somehow, or there's something else, going on. But you're able to, they work that out with trigonometry, because you've got an angle and the hypotenuse, and away you go. Another one, 2 skaters, Alfred A and Barbara B, skating towards each other, and there's a collision. But maybe deliberate, because they not only collide, they hold on to each other. They could be friends, who knows. Alfred is 83 kilograms and has that speed. Barbara is 55 and moving at that speed. What is the velocity after the impact? And so the momentum here in 2 dimensions is here and here. So if there's our momentum of Alfred and there's our momentum of Barbara. Put it together. Again, they draw these arrows here. It should be up there. And you've got enough information to work out. Because you've got 2 sides on a right angle triangle. Away you go. Now, if you want to see situations where momentum is or occurs on a large scale, but an inelastic collision is a meteorite hitting a planet is an example of an inelastic collision, because all this rock and stuff is deformed. This is Wolf Creek, not where the movie occurred, but an actual very well preserved meteorite crater in West Australia. And it's quite impressive. And the impact that caused this is a couple of kilometres across. The impact that caused this was 50,000 tonnes. And it's well preserved because in West Australia the geology there hasn't been much happening in the tectonic world in West Australia, so it's been preserved for quite some time, over 300,000 years. Now, work, energy, power, let's just wrap this up. Not much has changed, nothing much new in physics so far, but we will hit some new stuff when we do electromagnetic induction and things. But you expected to know all this. Work is equal to the change in energy, which equals force times distance. They throw in this cos theta, but it's always going to be, that's always going to be 1. Potential energy equals mass gravity times height, kinetic energy half mv squared, and power equals work divided by time. Okay, and just remember all your units. In physics, we don't give you a list of what all these letters stand for and what units to use. We mainly just to make it hard, but it's not too hard to remember such things. There's a fly buzzing around. If we looked at some graphs that we may be asked to interpret, we have force applied over distance, and so the area under the graph will give us the work. And that could be any shape, and we would be expected to be able to work out the work by working out the area under a force displacement graph. And then on your OneNote, you'll find lots and lots of videos. That's just a list of them. There's probably more now, and different ones that show work, power, energy, momentum, all in real life happening on your little screen. So that pretty much ends our revision section, I think. And so you should be able to do all the questions that you have to ask and be ready to start the next lot sometime soon. Cheerio.